Yeah, please record. So this is really Muskogee. This is Oklahoma. This is really Muskogee Nation, and so the story goes as follows. So there are the animals in the forest, and there are the animals with teeth, and then the animals with wings, and they decided they're going to play a game to see who is going to be the winner of the forest in that area. So the game they're going to play is called ball stick. Basically, you have a pocket, which is neat, and a stick, and so they're going to pass the ball, and so all the animals get together. They're going to make the teams, like we make teams out in the field. And so there's the animals with teeth on one side, the animals with wings on the left side, and there's an animal that's in the middle, a tiny little animal that has both teeth and wings. And that's a bat. So the wing says, "No, you're really..." Animals with wings says, "No, we don't want you in our team." The animals, the lion says, "No, we don't want you. You're tiny. What are you going to do?" But the bear says, "Okay, we'll let you come with our team." And so the bear gets the bat to sit on the bench with the teeth animals. So the game goes on, and for a whole day they're just fighting, and they're about even, but it starts to get dark. Still, the animals with the animals with wings, the birds, are winning the game. So at some point, the little bat goes to the bear and says, "Can I go in? I can fly in the dark." So the animals with teeth allow the little bat to actually get in the game. Now it's completely dark. No flying animal, no bird can see where they're going. But of course, the bat can navigate itself, and they win the game. So now the bat is really the most valuable player in the animal kingdom. And because of that, the birds, the animals with wings, had to be punished. And the punishment is, in the winter, they have to go away for 6 months south. And so hence this story, this is really the end of the story. And that's why birds go south to really in the winter. So
What about the owls? What about the owls?
Well, they don't play lacrosse. So that game that I described, the modern instantiation of it is called lacrosse. If you live in Maryland, in New York, in Colorado, and maybe even now California, it has become a very popular game. I will show you a scene from this is club lacrosse championship game between Maryland and Ohio. Just to get an idea of what this looks like, I hope I can display this. Hope it doesn't show, forget about it. I'm not going to show you. Ask me later and I will show you. The upshot is that, next, oops. Maryland actually won the game, and they are national club lacrosse champions. And some people may recognize this guy here. This is Jordi. He was in the last year. He plays lacrosse, and he was one of the co-captains of the team. So we are really excited. This is club lacrosse. In Maryland, they have an amazing Division I lacrosse team. And so unless, nobody can really make the team. So, but their club lacrosse team is probably as good as any other regular team in any other university. So anyway, popular game. Fast forward. Echolocation with bats. So bats emit sounds and they echolocate. And what does it mean to echolocate? You send a sound and then you measure how much time it sounds to come back, a little animation. And from there, you can estimate how far the object is that you are trying to locate. And typically, echolocating bats, typical bats, most of the bats, except one, emit sounds like this. Sure. Hmm? No, it is the same. Yes.
Yeah, slowed down, right?
Yeah. Yeah. So this is different vocalization. And that's how they chirp. So if you go over the lake at night, you're going to actually see bats. And if you could hear at 40 kilohertz or 50, 60 kilohertz, or have a device that actually can convert down, that's what you're going to hear. However, there's another bat which is called a horseshoe bat, and the horseshoe bat does not look for prey by flying around. What I call it is a lazy bat, and this lazy bat sits in the foliage and emits sound, and if it sees, if it detects something that is worth pursuing, like a big moth, it will go and actually move and capture it. So the vocalization of the is louder. Very different than the previous vocalization. And what's the difference? Is that the vocalization here is a continuous wave. Okay? So this bat sits there, emits a continuous wave. A little moth comes in the way, interacts with the wave, and a signal comes back to the bat's ear, cochlea, and then from there it knows whether it's a small moth or a big moth. So in fact, this is really pretty remarkable because this is the first paper done by the Schnitzler group in Germany at the amazing Tübingen, University of Tübingen in Germany. Europeans are amazing in neuroethology, studying behavior of animals in environmental understanding. Yes.
But you mentioned the Japanese Suga, I think it's Suga that did all this fantastic work on these bats, right?
Not this one.
Not this bat.
Not this bat, not the horseshoe bat. Suga did all the work on the bats, a lot of work on the bats. But the horseshoe bat was studied by Schnitzler in Germany. And basically what he saw, he did experiments and he basically detected the signal from the recorded signals from moths. These are four different moths. And it looks like the animal is able to actually localize, detect what kind of moth you have flying in the air. And so another feature of this is basically the cochlea of the horseshoe bat has a phobia. What it means is that you have the frequency band, a distribution of filters, and at about 80 kilohertz, you have a high density of filters around 80 kilohertz, much like our phobia involves that photoreceptors which are really densely populated to really have high resolution. So what's going on here? What is the physics behind it? How does it detect what species, what moth you have flying there? Well, perhaps a good start point would be the Doppler effect. And a Doppler effect is if I have a stationary observer and a moving source, where is my here? You're going to see that what the observer observes is that the frequency of the source increases as the object is coming towards you. If you're in Europe, where we have a lot of trains, you start at the train station and you hear the train coming by and go, ooh, as it goes away. That's the Doppler effect. Now, you don't need to go to a train station to see the Doppler effect. You can actually see in the ducks in the lake, as the duck, in this case, is not a duck, but as it moves through the water, the waves in front of the bird gets compressed, and that's actually the Doppler effect too. As it moves, you get compression of the waves, and so that's exactly the equivalent. So now, having talked about the Doppler effect, we talk about an observer that is moving, and you have the echolocating, the horseshoe bat is sitting in the leaves on the tree, and it's doing nothing. So now a little moth comes by, and big moth flaps wings slowly, small moth flaps wings fast. So how can you tell now? And the moth is moving. So what's happening now is that you have the Doppler effect of the body of the moth, but also you have a Doppler effect from the wings that move. So that is called microdoppler. So on a moving object that is articulated, you get a composite Doppler effect, signature, reflection, that actually allows you to tell what it is, how big it is, and what not. So, yes.
Can a bat catch a moth? The moth is stationary.
The bat can catch a moth when it's stationary. In fact, the psychophysics experiment they have that they did later, a very nice series of experiments by another junior professor in the same institute. They set up this little box with moths, and they have the bat, the echolocating bat, and they have the moth moving like this, hang from a string. And if the moth is small, the bat doesn't go. And if the moth is big, the bat goes and catches the moth. And so then they did a model. In this case, the moth is actually not moving. Yes, you can catch the moth. The answer is that.
Even if it doesn't flap the wings?
If the bat flaps the wings, no. It won't go because it doesn't see anything. So, right. So if it's stationary, no. Okay, that's what you mean. It has to, in order for this to work, the bat needs to detect something in the sound that tells it this is a moth and this is a big fat moth.
So if the bat would be catching the moth in a real environment where you have a lot of clutter, like leaves could be moving, there could be some other animals which are not of interest to the bat.
Right, but in this instance, when the moth is flying and the bat is sitting there in the foliage, there's not really much around. There's many moths of different sizes. Yes.
How does this horseshoe bat detect the range to the thing with this continuous wave? How does it detect the range if it's continuous?
Well,
not a chirp.
Yes, that's really a good question. It can change vocalization, but it's mostly, when it's just sitting on the perch there, it's just emitting continuous wave. Yes. So moving on. So the acoustic Doppler and the microdoppler, basically, this is really, I'm giving you a schematic description. You have a bat here, it's emitting a sound, you walk, your body velocity is v, but your legs are about 2v, twice that velocity. And so when you get a signal on the receiver, you get a signal which is really a very weird composite mathematical model. It's not an FM signal, it's not an AM signal. It is a modulated signal that has to do with some phase, which is a function of time, amplitude modulation. Anyway, what does it look like? Well, we actually thought about this Doppler effect, that this should happen, and we actually did some experiments, and we wrote the first paper of microdoppler using acoustics. For unbeknownst of, we didn't know that the body is doing what it's doing. Okay, this is really one of the things that you do that experiment, you're surprised nobody else did it before, and then you get measurements, and basically this is really the results of a person walking. This is a 40 kilohertz sound. So you have a signal of 40 kilohertz, and this is 4.1. This is 41 kilohertz and 39 kilohertz. So very. So this is an expanded view around 40 kilohertz, and what you see now is that the person starts walking. You see these waves, and the red line corresponds. This corresponds to you walking, your body walking. As you walk, you accelerate, you decelerate, you accelerate, you decelerate. So a walking pattern is at a constant velocity, but there is a little bit of acceleration on top. The scalloping this large scalloping here is due to your legs, okay? And the small scalloping here, this and this and this, is really caused by the thighs. So, and also if you move your arms, you're gonna see your arms there too. So the bottom line is that the bat, or our acoustic receiver, looks at something like this, and from here, you infer what it is and how big it is, and what are you doing in the instance, or in our case. So
how far was the source from the subject?
I mean, this is really, the source is here, someone end of the room, walking within a room. So we did this experiment, and we actually went and also look at animals, and this is really how a small pincher dog. This is the microdoppler signature of a small pincher dog. This is the microdoppler signature of a pit bull, and this is a microdoppler signature of a horse. So from the signatures of acoustic signatures of the animals, the bat was able to know what animal it is and where it is and what not, which is really consistent to the story, the Indian story. Now, we also built a foveated cochlea, a silicon foveated cochlea, and then we compare the outputs. We had a robotic moth, and we flapped the wings of the robotic moth, and we recorded sounds from the acoustic transducer. This is really doing a spectrogram analysis around 40 kilohertz. This is really using the foveated cochlea and FPGA in this case, and you can see we're getting very, very similar results from the bio-inspired filter bank, essentially, instead of doing FFTs. Yes?
Sorry, can you just remind me what the difference is between a foveated cochlea and some other kind of cochlea?
Okay, so a cochlea typically, I need to go back.
I'm sorry.
No, yeah. It's this. A cochlea will have a neurons per octave is how many basically channels you have out of the cochlea. You have actually a uniform distribution across the filter bank. And so, which this is per octave, which is doubling the frequency. So you really is uniform in a log scale. What you have in a foveated cochlea, you have a small frequency band, but you have a lot more neurons. because there you have to do very high resolution spectral analysis to detect the microdoppler effect.
Another problem I was having.
Or is that?
For a typical
Should work.
Yep. For a typical animal, this is really costly. This is
Isn't that my one error in the training data?
oh, fine.
It's just like the first letter is over.
Your microphone is on.
Okay.
Sorry, so I was just saying, so does that, so is that like the phobia in the eye where it can move towards the
No,
image,
it's
or
there.
it's fixed?
It's
at
fixed,
that-
but it's high resolution sampling of the sound
At that particular.
at that particular small area.
That's all I need.
Is that clear? In that sense, it's a phobia, not that yes.
But is it really step-like in that way? Has it ever been replicated? There's very discrete steps in the.
This is really the original paper. There's better papers that actually show better. This is really the original paper, which is really at that point, there were puzzles, how are these things happening? And also they look at the nerves coming out of the cochlea and say, oh, wow, this is really the first paper that I presented. This is amazing work, actually. I think this is,
So
It's not
Andreas,
quantized like that.
yeah, it's not, yeah.
so Andreas, if you translate it to the quality factor of the filter, what
Yes.
does that translate to for that?
I mean, you really, to do that, you really need to detect things at 40 kilohertz, that they are about 10 hertz resolution.
So that's a
Andreas, is there something special about that particular mechanical part of that cochlea, that back cochlea, that is mechanically different?
I don't know, but that's a very interesting question. I mean, the whole thing about this is one of the things, we are working in the lab, we discovered this microdoppler effect, acoustic microdoppler effect, we wrote a paper, we learned about the bug, we went and looked at it, and so this is a story which is really an interesting story, I mean, I think, yeah, and so, okay, so we also built a foveated digital cochlea using FPGA. And so now let me switch gear to doing generative AI at the edge. And this is really where I'm going to connect to generative AI. And just for those who are LLM people here, I'm not going to talk about LLMs. Generative AI has a lot of other areas, machine learning, which is not LLMs. Okay, and I'm going to address some of those. So if we want now, we want to take our synthetic horseshoe bat system and put it on a robot and have the robot moves around and recognize things and find distance and navigate without a camera. Okay, so in general, the framework that we're going to use is this here, where we do sensing, where we detect signals and from the world. We do perception, where signals are turned into symbols. And then we create knowledge. And I think this is really, in an embodied system, in an active system, that knowledge that you take a robot and you put in an arbitrary environment, you train the robot with some models so it can actually operate. But as it goes in the environment, the robot itself needs to actually capture information and create knowledge and create a model of what the world is that the robot lives. Otherwise, it won't be able to function as good as we do, because that's really what we do. I mean, we don't just train once and go somewhere and then operate. So so you have reasoning, information to action, and then behaving actions to work. Yes.
How tight do you want this loop to be? Because robotics, sense, plan, act paradigm is proven to not really work because it takes too much time to create this knowledge to activate in real time.
We can talk about that. It comes, the embodied structure has two parts, and both parts are computationally intensive, which is creating knowledge and learning abstractions and reasoning to form action. For example, planning to plan a move, okay, to move from one place to another place to another place. That actually is a hard problem. And so that's kind of, and we can talk about that later.
From a drone or a bat threat, they need to solve this problem.
Yes, exactly. So it's two tasks. One is perceiving and really closing the loop in that sense. The other is actually planning and doing actions. And LLMs can play a role in actually planning the actions. This is some really nice work. Anyway, model-based systems with composability to explain decisions. I think that's important. It's important to actually understand that. So let me now go back to the acoustic microdoppler, and let's do action. This is one slide, but it's going to take a bit to describe. Action and gait recognition at the edge in an embodied device without a camera, like a bat. So, and I have to make this comment because we wrote this paper and I sent it to PAMI. The first paper we wrote on this, a very nice paper. So the PAMI editor, associate editor, rejected the paper right away with the following comment: you cannot do action recognition without a camera. That's it. Paper rejected. So we take the paper.
What's PAMI?
Pattern analysis, machine intelligence is the most.
No, I just wanted to know which
No, no.
journal.
This is the most prestigious journal in machine learning, AI, whatever. Okay, rejected. So we submitted to IEEE Access, got published right away. It's really a lot of work, actually. I mean, it really is a very nice paper. And then I go to my colleague. I gave a presentation at Hopkins, and one of my colleagues, René Vidal, who is a big guy in the AI community, was in the audience, says, have you published that? Why did you send it to PAMI? And I say, René, he's the editor-in-chief. He was the editor-in-chief of PAMI. We sent it to PAMI, and it was rejected because they told us, you cannot do action recognition without a camera. Anyway, I mean, that's really, that's the story. So, this is a data set we collected at Hopkins, an individual doing actions. The actions about 15 actions, and it's about 10 individuals. At some point, we're going to turn them into also neuromorphic spike-based data sets so people can use it with spike neural networks and whatnot. But at this point, we haven't even shared this data set. The data set involves acoustic microdoppler, acoustic sensors, in three different directions, a camera and a Kinect camera.
Do you share it or you don't share it?
I'm happy to share it, and I think we should really publish it and post it somewhere. It's just one of the things that we don't have time to do. This is like 15 years ago. So this is actually the data collection unit. We actually brought that Telluride a few years ago, about 7-8 years ago, this unit, and we use it to do action recognition with the Alimonos Vermuller group, where we actually pick a stone or a cutting, actions of cutting a cucumber. So this is the sensing. For those doing machine learning, I'm going to introduce an idea here, which it may be very popular today, but it wasn't when we started it, and I think in this sense. So we have data from a Kinect, and the Kinect data is cloud data. It's a high dimensional data, okay? So we record the actions with Kinect, and also with sound, and also with a camera. So we have high dimensional data, and then for each one of these actions, which is Kinect cloud in time, we also have low dimensional data, and these are really a 3D representation of the microdoppler signature. Okay, so Kinect data on one side, microdoppler signature, one-dimensional data, low-dimensional data on the other side. So the model that we use for machine learning to really do action recognition without camera is the following. We take high-dimensional data, and that allows us to train models that will allow us to actually create scalable pose and action label. Essentially, we use the high-dimensional data to discover the language of actions, to create a language, a symbolic representation of the actions. we don't, Alimono's group, they pose that action should be composable. They wrote a lot of papers and they generate actions ab initio, so to speak. We say no. Actions is what people do, and what we need to do is discover the vocabulary of actions and learn the vocabulary of actions for this population that we have there. So we're gonna learn the vocabulary of actions, and then once we have that, we're gonna create a model, and then we're gonna use only low dimensional data to actually do recognition. Okay, so yes.
Rotational representation, spectrogram representation, are those also?
No, this is body. I'll show you. I will elaborate on that. So, perception, signals to symbols, the microdoppler effect. We get basically the signature there that you have here. And these are our models. So, our action models, basically there is as a collection of skeletal poses evolving in time that actually, and the way we do it, we look at all the actions, we do a K-means classifier, and we pick up the top 128 most significant actions. So we wrote this, we built hidden Markov models, we did mathematics, beautiful mathematics. We wrote a paper, we published a paper, and these are the results. And we basically, using this approach, generative high dimensional data for creating the dictionary, throw away Kinect, throw away camera, rely only on acoustic signatures. For all the different actions, we're doing about 88%. That's pretty amazing, actually. That's really 90%. For a similar data set, actually, with cameras, about 90%, 91%. For a small data, yes.
So can I understand this as essentially you are finding the acoustic features as opposed to the visual features, which we're used to thinking about, and then you're able, once you've identified what those are, you can just look for them and then cluster them into one gesture or another.
Yes, however, the important thing to point out here is, in order to do something and have models that are composable, you need to create a language, a dictionary. And what we have learned with the high dimensional data is a dictionary of actions. We learn the symbols that we should be using to classify the actions.
But what's the that actually
Yes.
is helpful, because what I'm asking is what is the difference between features and symbols?
Features is from the raw signal extracting some corresponding to the representation that hopefully doesn't loses information, that allows you to do the processing in a more convenient way. So taking a time series, a micro signal, making a Fourier transform, or making a filter bank or a Fourier filter bank, and you have 100 outputs. You have one input, 100 output in one signal in time, 100 outputs in frequency. That's a feature. Symbol goes above the features.
Andreas, about the gesture, this is a low frequency trajectory, right? I mean, what resolution are you looking at? I mean, it's not a periodic.
No, it's not.
So then you're looking at a shift which is like 1 second.
No, it's hertz. The shift of about 10 hertz, 2 hertz resolution. That frequency.
It has to be digital because it's a very.
You can do it in analog too. There is, yes, okay, I'll tell you one way to do it.
It was my recollection that the Kinect at that time is about 10 years ago, that Microsoft shipped a very nice API that basically extracted the skeleton for you. So basically you didn't have to do the heavy lifting of using the Kinect data. Just a minute, as my recollection, that they would deliver you the the human pose model.
Yes, we
They would
did.
deliver you all the joint positions.
Yes, we did.
So
That's what we use.
That's what you use. And
Yes.
I still don't understand, what's the pose, the human pose, how's that related to the Doppler
Okay,
signature?
yes, so, okay, you're gonna see the next slide.
Okay.
So
Just show us
Kinect, no, Kinect gives you the skeleton.
Yeah.
And we take all of those skeletons from different actions in time, and we do a k-means, and we find the first most dominant 128 skeletons that are really represent the action set that we have. The action, the data set
You're able to classify the action just on the k-means clustering
of the,
skeleton.
yes.
Then what's the microdoppler for? It adds.
Okay, yes. So at the same time now, we record the microdoublet. You're gonna see the story gets a little bit more complicated. And when we do recognition, we don't use the microdoubler, and we use a traditional maximum likelihood estimation approach where we have signal, we have language, and we need a language
Why do you need a language?
because we need the symbols.
You're classifying the action, right?
I know, but in a traditional maximum likelihood argmax, I mean, I have the equations.
But I thought you were using k-means to classify.
No, the k-means is to find the language. Once we have the language, we take those actions, and then every acoustic microdoubler signature comes in, gets classified in one of those 100 actions.
So well, you call it a language, but it's just a set of classes, right?
Well, it's
Why is it a language?
a language because each one of these class represents a different pose.
So it's just a set of poses.
Right, and that I call a language of poses.
But I mean, a language has to have a grammar.
You see, I disagree with you, yes. No, a language is a symbolic representation of something.
Okay.
It's more like a dictionary.
A dictionary, yes, if you want a dictionary. Yes. You're gonna see the generative model later.
As a generative model and a dictionary, I imagine it's more.
You're gonna see, just wait,
combination of-
let me go on. We haven't talked anything about generative model. Okay, not language, dictionary, okay. A symbolic representation that actually is a dictionary of actions. Okay? 88%, amazing.
So one thing, Andreas, in the complex, the phobia, how do you pick the frequency and the resolution that you need, or is it programmable?
Well, I mean, in digital you can do it. The animal evolved to have a foliated cochlea at the frequency that it vocalizes. I mean, 80 kilohertz is really where the part vocalizes, and that's where the frequency is. Okay. Now, after we wrote the paper and 7 years of work from Thomas, Mary, my graduate student, a summer graduate student comes in. This was the heydays of neural networks. I mean, mid-20s. It says, how about if we use some neural networks to solve the problem? So we took the data set, forget about language, forget about dictionary, forget about anything. Just get the raw microdoublet data signature. Forget about all the theory framework that I described to you earlier. And it comes and we take that, we build an LSTM model, we enroll the model, these are the model parameters, and we tested it, leave one out paradigm. What the fuck? 95%. It's just insane. Insane. And then if we, and with this is 800 parameters, at 1200, we get a little bit better. The point to be made is that after the guy spent 6 years doing mathematics and theory, we come back with LSTM to the right and beat the best model that we had by far, 95 and 95% for an 800 parameter. So at that point, you say, neural networks are very unreasonable.
But how many parameters did you have in this LCM?
Here are the parameters. 800.
And there's the other things, maybe you can compare their computational complexity and how well it generalizes to a different data set.
Well, okay. That's a good question. We have not answered that because we don't have microdoublet data for other data sets. But yes,
Can I just say that as an application, this is very elegant because it preserves the privacy of the people who are giving the gestures in a way that if you were using a camera, it would not.
absolutely. Absolutely. So we can, using LSTM, we can get 95% for action. Actions are more difficult than gestures. And this device costs $2 because it's and actually the more interesting thing is that most acoustic transducers, most speakers on their phones and most microphones on their phones or Alexa, they have a bandwidth that goes above 40 kilohertz. So you can use actually your microphone, your speaker on Alexa to do this without adding hardware. Okay, let's go to the generative. Yes, question.
My question here, so in this example, you didn't use this multimodal thing.
Nothing.
There's no connection
Just
here.
raw data recorded microdoublet data. And we beat by 6%. Almost perfect.
Just
Yes.
ground truth?
But when you have ground truth, because Kinect is a ground truth. Yes.
Like the dictionary.
Yeah, we have a dictionary, yes.
So Andreas, how would you compare this against millimeter wave radar?
Very good question. So for many years, Google had a project called SOLI project, where they use millimeter waves and use microdoppler, but in the frequency domain. A 10 gigahertz signal that is about 10 centimeters. So 50 gigahertz is about 2 centimeters. A 40 kilohertz acoustic signal is a millimeter. So we have higher resolution from acoustic than we have from RF. So we actually can do better than that. Anyway, move on. So this is, we tried, these are the results. We had a product of experts, and this is really the test. The bottom line is that the start HMMs, which is really what I described before, 89%, and the LSTM 800 and LSTM 1200, 95%. One by far. So at that point, we say, forget about science, just do neural networks, just. Okay. Learning at the edge. So we built this thing with neural networks and we deployed at the edge, and someone has wants to introduce new actions. Well, if it's on the robot, ideally you want the robot to actually collect data, create a model, and understand that there is new actions and whatnot. And in this case, because we only have microdoppler, we cannot really have Kinect on the robot to help us create new actions and whatnot, or just do blind data collection, because I don't think that's really the way to do it. So what we're going to do here, we're going to have the machine use generative AI to actually create new data that can be used to train a model online on the robot, not in the cloud. And we can enroll new users, improve robustness, and alleviate data center energy expenses. Amazon spends $10 billion a year training models that come from Alexa, and that's a total loss because they never made that money. So what Amazon wants you to do is, if you're using Alexa at home, they want you to spend the energy at home training models at home on your device and not in the data center. So the challenge is that if we're going to use this model to actually try to make a generative model, when you are deployed at the edge, you don't have the Kinect data, and we need to actually create a generative model to create new poses that you haven't seen. So this is the other half of the story. So now that we built a skeletal, even though Kinect give us a skeletal model, we built actually our own physics skeletal model. And also we built physics interaction between the skeletal model. So we can actually turn the skeletal model into microdoppler returns and use it also in a generative model. So this is really the framework that we use. And I'm gonna start with that, where we actually have a skeletal model seat, and then we put in the generated model. You're gonna see what model we're gonna use, and that generated model is gonna generate additional data that can correspond to a big, tall person, short person, fat person, big moth, small moth, whatever. So the generative AI model we're going to use is going to be a conditional deep belief network. It's a class of models that came in the mid-2000s. Actually, they started in the 90s, in the early days of neural network. And so basically, what you are doing, you start with a conditional deep belief network, and you have this conditional random Boltzmann machines, which is really the key in this model. And so then you unroll in time like we do today, and we train. And so this is really a generative model. You don't hear much of it today, but under the hood of a lot of what is happening today, you're gonna find models of this sort that they're not as sexy and they're not more, but I think this is really what it is. So in the case of let's start with the physics model. This is what was said earlier. We can have a person. We can actually send a wave. We have the equations there. And as the person walks, we can actually get the microdoppler return from a physics model that we generated, okay? Now, because we generate the physics model, we can put parameters on the length of the arms. I'm talking about actual recognition here, but you can take this and translate it to a moth. How does a bat learn a new class of moths that are in the environment, okay? That have to do with the size of the wings, how fast they flap, and whatnot. So, and what you see here now is basically hallucinating skeletal poses from a seat, and also microdoppler returns. So now that we have this model, we can use the conditional deep belief network to actually to hallucinate novel microdoppler signatures that we can use now to train a better LSTM model eventually to do better performance and adapt their performance. So we actually go from a generative model of actions into actually microdoppler signatures. And that now we have knobs, we can program how big the person is. Yes.
And could you then use it to generate gestures that are easily differentiable from your existing dictionary of gestures?
Exactly. If you want to create a new dictionary, yes, you can also do that once you follow this framework. And so now this is another example of actually, it does very natural. The person walking, it does look natural, but this is totally generated by AI, by generative AI. And the last one here, which is another action. Oops. Yeah, raising the left arm or the right arm. All of it, both actions and microdoppler signatures, which you're going to use for the model to train new models, are generated by a generative AI model. Now,
how about the acoustics of the room and everything?
Okay. Let's
complicated. Why is there 3 plots?
Huh?
Why is there 3 plots?
Oh, this is different actions. One was
The three.
because I didn't explain that. Sorry. When we're actually recording from sound, we have a sound a transducer there, a transducer here, and a transducer behind in 3 different frequencies: 28, 32, and 40 kilohertz. Yes, sorry, I should have explained that. So now, I just said that basically our models hallucinates microdoppler signatures. Hallucination is bad. Well, not if really is what your goal is, to really create data sets. So this is real microdoblet data. And this is microdoblet data from a hallucinated, we seeded it with that, and we know what the action is, 2 limbs and whatnot. You cannot see it here, but I can. This data here is missing a limb. Okay, so it hallucinates data, but there's a limb missing. And we cannot solve that. This is the same hallucination problem that you have in modern AI when you do generative AI. And so, or it was funny, I think the example, I couldn't find it. We got this wonderful microdoblet data of someone walking, and it looked like the person had a 3rd leg. And you could see the 3rd leg in the walking pattern and just say, this is not a human, you know? I couldn't find that example, but yes, so that happens. For those who are going to have that question. So this is really all the papers that describe this work. And so I hope that this story helps see generative AI in a slightly different framework, one that actually can be used at the edge to create new data sets, to enhance the data set, and do training and improve your performance and adaptation and whatnot. And finally,
Andreas, I have a
yes.
question on.
By the way, this project started, this is a result of a project that started in 1990, 2004 or something. It used to be a European project, Scandal. Giacomo was part of the project with Sue Denham at Southampton, and it started in a hide up Sneffels, the one that you guys were in last week, in a tent. I shared a tent with Sue, and I said, Sue, we should really try to put a European project together, and that was a project that led to all of this work. You can see Sue Denham, and I mean, it's really one of these projects that. Anyway.
So Andreas, about this data, like, how can you get a 1 kilohertz Doppler shift for a gesture, like, you know,
This is 500 hertz.
kilohertz, right? So
No, 500 hertz. Yes. The baseband frequency is 40.
And so there's a peak.
At 500 hertz.
Yeah. So
corresponding to the velocity.
Isn't that a pretty high velocity?
No, yeah. Your arm moves very, when you do this, your velocity is pretty high. So that's really, we have accelerometers and we measure velocity, and really this is validated by, yes. Yes.
One question on the system level. So in my master's, I also worked with basically acoustic, ultrasonic sensors, and I did a comparison for my application with pulse echo versus continuous wave. And in the end, it turned out if you apply the algorithms on a really low power hardware, that the energy you need for the excitation of the ultrasonic transducer when you use continuous wave is much higher than the power for the actual algorithm. Is this also something you saw, or? Yeah,
yeah, but the continuous wave, you're not going to be really transmitting continuously. You're going to transmit like the bass,
pulse wave,
pulse width modulation, where you're going to transmit quiet for a while, transmit quiet, and so that duty cycle actually reduces. Yeah, but that's part of sensing. A microphone is a very expensive device. All of these people building AI hardware to do keywords recognition, and unbeknownst to them, actually the pre-amplifier to the microphone they're going to use for doing that is going to be about 20% of the power they're going to use in their algorithm. I know the number because we measured it in the lab. So sensing is expensive. And active sensing is expensive, and it allows you to do all kinds of other things that you cannot do with passive sensing. Yes.
Two things. One, somebody mentioned room calibration. I'm assuming you could do some you could have a calibration step that would tune the system to a particular room. So if it was on an Alexa, as you've been talking about, you could.
Let me respond to that. So for sound in the air, the loss, the attenuation loss goes as a power law to the third. So really, if you're sending sound and you're gonna localize sound, first of all, you have a narrow beam, you really don't look at on the surrounds. And the surrounds don't move. That's the beauty of it. The surrounds don't move, so it doesn't matter. What you are really detecting here is velocities. You're turning the moth as something that corresponds to velocities, slow moving up and down and fast moving up and down. So I think it's not never a problem. And also, yes, you can do this actually at a kilometer. We had a transducer that we could actually put 200 watts and send sound. Yeah, but it's not, yes. Yes.
I think it's very nice to train the model with the generative AI part, right? But
Yes.
you need less actual data, but the problem is you then need a shitload of data to train the generative model, right? And so I think the real kicker why this works is because you put in the adaptive bias of the skeleton. Like if you didn't have that, right? If you get a complete black box model, it's just trying to predict audio from video. I
No,
think
no,
you need the same
no,
data.
you miss that. The generative model takes a seat, which is so much from the acoustic mic, from the micro Doppler. So you don't really need a lot of data for training the generative model. And
But it's not clear to me why you need the generative model at all if you have the physics simulator in the first place. It's just not so expensive.
because we want, no, we do have a physics simulator and you're gonna use it that. But the physics simulator will not give you nuances and natural, it will give you basically these poses that are really kind of very robotic-like.
But why can't you introduce domain variation?
Yeah, you can introduce domain variation, but I think that the generative model actually does it for you, introduces noise and introduces actually variability that makes
But
it more
maybe
natural.
not in the directions you want, right? That's why it's.
Yeah, yes, I agree, I take it, yes,
There are
yes.
several ways of doing it.
Yeah, I mean, I wanted to make the point that actually there's more than LLMs and DALL-E in generative models, which are really.
And maybe that physics simulator is very expensive to run, right?
Yeah, I mean, yes, well, not really, I mean, we run, it's very, yeah, I mean, yes.
That's exactly what I mean. Like the reason why this generative AI model works so well is because you have the step in between where you go through the physics.
Physics model,
with
yes.
the skeleton. That's the important part. If you replace it by just a black box model,
No,
this wouldn't probably work.
it wouldn't work, I agree. The physics, and that's the point I was trying to make there, we need rounded models of reality in an embodied environment to actually have robustness. Yes, yes.
I just wondered, so the last paper was 2017, so is
Yeah.
there any, I mean, I hear funders talking about the difficulty of anything happening with all this great research that's being funded.
I mean, there's a pattern after that.
Okay, and anyone licensing it?
No, because we didn't pursue it.
I mean, no, but I think it's worth commenting that, suddenly this is greatly simplified, right? You have a whole human visible to the sensor, it's right in front of the sensor that people are doing very stereotype motion. It's a very different situation in a real person's house with all the furniture cluttered around.
But the furniture doesn't matter because it's not moving.
No,
remember.
there's reflections off all the.
The reflections not moving, anything that doesn't move doesn't get involved in the model.
Okay, so you're saying, and also you have to have multiple receivers, right? Otherwise you can't.
You can do that for gestures, we can do gestures and beat any other
If
kind of.
somebody's hand moving at a long distance doesn't produce much of it.
No, we do. Actually, the original project, Toby, the original project in one of these papers in 2000, whatever, we had a demo, the demo for Scandal, the final demo. Someone will come in front of this system and it will do a set of gestures and it will say like stop. And then the system will learn and then you can actually run the system to actually recognize the gesture stop.
But that's different than somebody sitting on a lazy boy.
Yeah, I know, yes. Do I think this is commercially viable? Yes, I do think it's commercially viable because of the zero cost.
Yeah, that's sure it's low cost.
Yes.
So just to kind of help with that, I think the reason that if you don't worry about the stationary objects is that if something hits a stationary object and reflects, it's the same frequency. And you're already pretty much getting rid of the center the center frequency you're transmitting, you're looking for everything around it.
Exactly.
And so that's why you don't worry about the stationary objects.
Yes.
Is that, yes,
And also we had, for those who, what else we didn't, but we didn't publish it because it really didn't work as good as it should have been, and maybe we'll put it next year as one of the projects. We had one of these drones, the tiny drones, crazy flies, with one of these transducers. And we had a moth who was supposed to go and detect the moth in the room, and the drone was supposed to go and find the moth and just sit on the platform next to the moth. This was a class project I did last year. I think they did 80% of putting everything together, but never got rid. But that's another project we can do next year. I think it'll be a fun project in perception action. Yes.
What do you think about moving this to sonar?
Two.
Sonar,
Well, this is sonar.
yes, but underwater.
Oh, yes, yes, it's been done, and it's been very useful, and it's been used by various places. Yes. Did I answer your question? Yes, the government and the government's care about underwater things that move. And so whether they are dolphins or whether they are divers, and so that thing has been taken and been exploited for that. Okay.
Okay, I'll start again. Good afternoon, everyone. I'm Raj Kubendran, an assistant professor at NIC department at University of Pittsburgh. And I'm going to give yet another talk on event-based vision sensors. Hopefully a different perspective on what I believe vision sensors can do, especially event-based sensors in the future how they can be integrated into mainstream computer vision pipelines. Okay, so with that, I'll go ahead and get started. So the outline of the talk today is I will take maybe a shorter history tour of what is event-based sensors and how they can be used for next-gen computer vision. A quick comparison of traditional imagers versus DVS. This is probably something maybe redundant here. I'm going to hopefully skip through this fast. And then I'll talk about my contribution here, the query-driven dynamic vision sensor. So this is what my PhD was based upon, and I've been modifying and developing further versions, upgrades on this. I will show some QD-based applications and demo with the actual hardware camera capturing gestures, motion detection, and traffic monitoring on the live, like on actual highway, superhighway in California. And the second part of my talk is going to be about scaling up. Like, how do we scale up camera architectures to go higher resolution and a higher speed of even throughput, right? So we are talking about greater than 1 million pixels at least. So we want to go 10 million pixels or more, which we currently don't have. There's no DVS sensor that can do multi-million pixels. I'll tell you why that is the case. And also about getting an equivalent frame rate of 10,000 frames per second or above, 100 microsecond latency between events. So I did some architecture study there. I'll present some results. So primarily what I'm proposing is something called a GALS architecture for event scanning, globally asynchronous, but locally synchronous architecture, which I think has a promising results based on the study we made. We found an optimal partitioning as to how much local is local and how much global is global, right? So we need to partition between local tiles and global grids to scan events as fast as possible while going for multi-million pixel resolution. And I'll show you some simulation results we made on that, and these were implemented on an FPGA as well. And finally, I have a plan for next year at the Telluride workshop where there's a sensors topic area. We can design an open source DVS camera. We can try different architectures, different scanning methods, and hopefully have some fun tape out of a chip within the 3-week timeline we have. And I'll summarize my talk. Okay. So starting with introduction, I'll probably go a little bit fast. So we know that computer vision with AI has come a long way. It's been changing how we sense, process, and perceive what to make out of it. So a computer vision system usually consists of a sensor, processor, and an algorithm. For an example, there's a high definition camera followed by a GPU. GPU implements a AI model or maybe some of the conventional signal processing too. Computer vision systems are increasingly pervasive. We use them like every day without even realizing, right? It's their autonomous navigation, smartphone camera filters, features, security surveillance, and automated industrial assembly. So AI with deep learning algorithms have truly revolutionized computer vision pipelines. We can do a lot more that we could not do like 10 years back. So we're getting superhuman performance in many, many tasks like image classification, motion tracking, and all of that. The future prediction, which is not future anymore, it's already here, I guess, is integrated computer vision to enhance reality, right? AR and VR. In short, we'll have AR, VR glasses soon. I don't know if people tried Apple Vision Pro. It was truly an outstanding piece of engineering. Of course, not at all affordable, but I think that's where the future is heading towards. Is we'll have sensing vision sensors everywhere, ubiquitous, feeding us what we want to see. It changes our reality, right? Of course, the current computer vision pipelines using the traditional cameras and traditional processing has limitations. They are mostly high resolution data captured at really high speeds and shuttled through like gigabit per second link onto a downstream pipeline that has to do a lot of number crunching to only find out that most of the data is useless, right? It's redundant data. We are capturing the pixel information again and again, even though there's no new information stored in them. And the onus is on the downstream GPU or whatever high-end computing machine is to throw away almost 90% of the data most of the time to compress the video stream, which is like taking probably a terabytes of data into something that's manageable in megabytes, right? So that's why a movie, if you want to have a 4K movie actually captured in raw data, it's just going to be impossible, right? Only when we compress it, we can store it in a hard drive. And the compression, what does it do? Is it ignores most of the captured data. So the sensor is just doing so much extra capture just to be ignored later. And that doesn't make sense, right? So humans, of course, we can recognize objects efficiently under extreme variations of illumination, orientation, distortion. There's a lot of different aspects that goes on in biological vision that is still not being captured in a mainstream computer vision pipeline. So we also perceive depth. We can do visual attention, all kinds of gaze-based tracking and all that. So there's a lot of scope to improve still when it comes to computer vision pipelines, especially for edge computing and IoT. So we need to develop a new sense of class of sensors, like the DGS camera. That's like one of the possible class. But we could go beyond, hopefully. We can take a lot of inspiration from distributed networks with sparse activity that we see in biology, in neuroscience, and also now we see that in machine learning as well. So this is kind of what my current research is based upon at PICT. So I try to do the bio-inspired computer vision pipeline. So I work on vision sensors and computing memory processors, and also event-based algorithms that can actually process the data and perceive something, right? So the idea is to end up doing visual perception, which is notice that there's a hand. Is the hand moving left or right? Or what does the hand mean? Does it mean a symbol? Like, does it mean stop? Or does it have some gesture recognition kind of a perception going on? So this is what I work on all aspects of these, but today I'm going to more focus on the vision sensor aspect. So we know traditional CMOS imagers use a pixel array. Again, I'm going to skip through this quickly. So we have photodiode that converts in photocurrents into a voltage using the photoelectric effect, thanks to Einstein.
What's the electric effect? Photoelectric effect is something else.
It doesn't matter. They convert light to electrons.
Okay. Yeah, the light electrons, that's where we establish a reverse bias voltage to establish a photocurrent, right? Okay, maybe yeah. Okay.
This is not how the NPS works or CMOS panels.
Okay.
They don't operate based on the photoelectric.
Okay. Let me just stop. Then it just converts photocurrent. We get a light converted into a photocurrent, and the VPH voltage, the photo voltage, is then multiplexed between rows and columns and taken to a external A to D converter outside the array, but still on the same chip. And that ADC does all the heavyweight, fast conversion of the analog voltage into digital output, and it has to be sent out as real fast as possible, especially when you're talking about larger arrays, right? Multi-billion pixels. The pixel is kept very simple here for the APS cameras. It has a photodiode and maybe 3 transistors, one to reset the photodiode, one to select that particular pixel. and one to buffer or amplify the photo voltage before sending it to the column line for sensing and further conversion into digital. So this gives you really high-speed scanning, the frame scanning method, where we choose one row and scan all the columns out, and we keep repeating that over different rows. And then we do a round robin back to the first row once we finish scanning one frame. So there's a high-speed scanning method, but there's a low sensitivity and there's a fixed pattern noise due to variations in the pixels during mismatch. Whereas retina, or the biological vision, it's a completely different modality. We don't have a frame scanning method. We detect changes, or we detect light using a photoreceptor based on cones and rod cells in the retina and in the fovea region. And the rods are sensitive to low light for dark vision, whereas the cones are color sensitive, that they lead you to detecting the different wavelengths of red, green, and blue. But there's a lot more happening in the retina than just detecting the light intensity. It does a lot of processing at the sensor itself. We have the horizontal and bipolar cells doing spatial high-pass filtering, the amacrine cells doing the temporal high-pass filtering, and there's further encoding of the information. So once you filter these signals out, we have the retinal ganglion cells that do spike rate or temporal even coding and sending the spike frame onto the optic nerve that goes to the visual cortex for further processing. So this is a completely different domain, different way of looking at how to capture visual data, right? And that's the inspiration for event-based vision sensors. And I actually adapted this work from the event-based neuromorphic systems book. So I think you can see the reference below. So I want to mention that what are the different types of event-based vision sensors possible? Because all of us usually talk about DVS all the time, but there are proper ways to classify this, right? Asynchronous event sensors are pixels that can generate events locally and be sent out with immediate relevance. So we have a first come first served basis as to who raises an event and how we send that out in a completely asynchronous fashion. The other class is a frame of event sensor. So we can still capture events in a frame scanning fashion, where we scan the frames and then only detect events in whichever pixel is producing an event. We capture that and then we send it out as a frame of event output. So I just denote these acronyms here because we're going to use that a lot in the following slides. So in general, silicon-inspired, bio-inspired silicon retinas are broadly classified into two types of sensors, right? The temporal contrast sensors, which is what the DVS does, is to capture the changes in time. So whenever the pixel gets brighter over time or darker over time, we capture that change and encode that as an on event or an off event and send it out, right? There's another contrast we can naturally do, that is spatial contrast, which I think all the previous generation of neuromorph engineers know about SC sensors, but maybe not the new generation. There's a lot of work done here to do spatial contrast sensing as well, where we detect the change, we compare the pixel to its neighbors and see if that center pixel is brighter than the average of the neighbors or darker than the average of the neighbors to generate a spatial contrast. What is that used for? It's used more for edge direction and contour extraction. So temporal contrast sensing is great for motion direction, for moving objects, but for static objects, spatial contrast could be helpful in quickly capturing edges and contours and do some post-processing to that. Yeah.
I thought the event-based cameras used to do both, and people somehow stopped doing the spatial contrast. Is that roughly true? So is it just an argument of pixel size? Like you can get smaller if you don't.
Yes. So yeah, detecting spatial contrast at the pixel level tends to be more cumbersome and more bulky. But yes, that's something we can approach again. So I want to go back to seeing if we can do a better job at or given the more advanced technology nodes, we can probably afford to do spatial contrast sensing now again. So the more famous vision sensor is the dynamic vision sensor. I think everybody's probably familiar with this. So that is an ATC sensor. So now we have acronyms to classify. It's an asynchronous event sensor that senses temporal contrast events. right? How it does that, it has the basic circuit diagram of the pixel with the photoreceptor based on Carver Mead's original design back in the 90s, and followed by a differencing circuit and comparators, right? And we have the folks who invented this here, so I'm going to skip through this quickly here. So the pixel design is able to capture the log, the logarithm of the photocurrent, and do a differencing circuit to capture the change in the log of the photocurrent intensity, the light intensity. And then the differencing circuit is given to a bunch of comparators that detect an on event and an off event using an on threshold and an off threshold. So when we have a smooth moving photovoltage, we try to detect discrete changes. Whenever the photovoltage goes up by delta or goes down by delta, we create an event that's an on event or an off event that is sent out as through asynchronous handshaking to the outside world, right? So it's something I think most of the people here know. But just to do a little bit of history, the DVS camera then gave birth to the Davis pixel, which had both APS and DVS kind of combined. So we had both the AETC version, the asynchronous event sensing temporal contrast. Also, we had the frame-based intensity capture in one single camera. Yeah.
I have a question.
Yeah.
Why do we create more acronyms to be able to remember more things?
I thought this would be helpful. If it's complicated, right? It's okay. You don't need to remember the acronyms. Yeah. This is just to show that there are different types of vision sensing possible, right? When we look at only APS and DVS and then call it that's the end of the story. It's not the case. We have had other vision sensors in the past, and we should probably revisit them again and see if we can do something new now. Yeah. So here we can see that I think that's it's a classic shot, the tennis shot shown where.
By the way, do you know who that is?
Totally.
You broke the system. I want to ask. I want to ask that. Everybody knows this already.
That was the most important thing for me.
Yeah. Okay.
Because
yeah,
they know what it is.
Yeah. So the same thing with the ATIS pixel that can give you a regular frame output as well as a DVS output, where we see the person who's walking alone are registered with a temporal contrast events, whereas the background is all removed out, right? But we also have other sensors. There was a model of the Parvo-Magno-Tina model, which tried to go as biomimetic as possible, capturing the amacrine cells, the bipolar cells, and the retinal ganglion cells using an inhibitory excitatory network. So that tried to capture both TC and SC, a temporal contrast and spatial contrast at the same time. So, and there was also Weiss orientation sensor, which did a frame of events. It was not an asynchronous sensor, it did frame capture, but it only captured spatial contrast events. So they could capture the spatial contrast at varying illumination conditions. You can see the same picture when we have a global shutter, regular APS camera. Depending on how much exposure time we have, we cannot see the bright background initially, and then we reduce the exposure time, but then we cannot see what is inside the building, right? So we can only see what is inside the building or outside the building clearly with a regular APS camera, whereas the SC sensor can capture both in one shot, right? So
the reason it captured both is because it does local gain control.
Yes.
Not because it does local spatial gradient.
Okay.
There's another thing that
It was that was the design of Pierre-Francois.
Yeah.
Yeah, but basically it's time-based.
Right.
So they got this high dynamic range by basically waiting until the integrated voltage was decaying off a capacitor was across 2 levels.
Yeah.
And then they use the timing of that. But the problem with that is that when it gets dark, it's very slow.
Yeah.
So these are all still pictures.
Yeah, of course. These are still images.
Yeah, still pictures. That was also the problem with the ATIS.
Yes.
Basically waiting, they were counting the intensity by the time between 2 spike events.
Yeah.
Fine if you have a still picture, but if things would get dark, you have to wait forever between the spikes.
Yeah, but the reason that it captures both insides and outsides, it has to do with gain control, which is local.
Yeah, local. Yeah, it has a kind of local.
Yeah, not because it's spatial filter.
Yeah.
Okay.
But there's a long history of all this. Too much to go through this time.
Yeah. So I'm just trying to introduced to a new generation that there are a long history of sensors out there. And now we can talk about like what kind of sensors we can develop in the future. So this then brings to the next part of my talk, which is the query-driven DVS camera, which is something I worked on. So what does this query-driven vision sensing do is we can compare this with the other traditional sensor architectures. So the APS camera, the frame-based scanning, uses something we have seen before, like we have a fixed delta time, right? The frame rate tells you how much a discrete time at which we get a frame worth of data. For 60 frames per second, we're talking about 16 millisecond delay, right? Delta T is fixed at 60 milliseconds. So we do not get any information in between. So if something drastic happens in those 16 milliseconds, we can't capture. We have to wait for the next frame to arrive to make sense of what happened, right? This is done with a relatively simple pixel design. As we mentioned, it's just a photodetector with a reset transistor and a buffer. This is used in most of the modern cameras out here at a fixed clock rate and to continuously stream out the pixel intensity data. The problem here is we have a high dynamic power consumption because we are reading out the buffered voltages through the columns all the time and converting it into a high resolution A to D output, right? So the ADC is working all the time at hundreds of megasamples per second. Hundreds, I mean,
Why?
Because we have to scan a million pixels, right?
Nice.
Of course, the people use multiple ADCs to kind of balance that out, but that's a traditional approach. We try to max out what the ADC can do, consuming dynamic power all the time to convert them. And the pixels themselves do not consume, they only have a minor static power at the buffer, but the dynamic power kind of dominates in such a camera. Whereas the event-based dynamic vision sensor, I just denote it as EDVS just to distinguish between QDVS that I'm going to talk about next. So this is a complete rethink of the vision sensing where we don't capture frames. We are sending out asynchronous packets, right? Event packets that have X, Y, TP information, the row address, column address of the pixel, and the timestamp at which the event occurred, and the polarity of the event, the on or the off event. So this is a completely different way of looking at the data where the delta T is variable. So we can receive events at a much lower latency as and when they occur. And if there's no events produced, we don't need to scan them out. So we can just wait until the next event happens. So this is a great way of capturing a temporal contrast and not having to do any redundant capture. But the problem is the pixel becomes larger and it has to do a lot more functionality within it. So it has to monitor itself for changes in the photo voltage, detect the event, and send that event out through a handshaking scheme. So there's a lot more circuitry involved, which adds up to the static power. So we have a preamplifier and a bunch of comparators that take some static power, and when you scale up, that's going to be not negligible anymore. And to add that, we have digital AER handshaking, which generate the row request and the column request. So every pixel that has an event reports, raises its hands up, saying, I have an event. So every pixel is autonomous in that sense, and it can raise event request anytime. And it's the job of the arbitration scheme and the downstream pipeline to acknowledge these requests as and when they occur. And this is good when there's low activity in the scene and we're talking about smaller resolutions. But when we have a lot more pixels and a lot more events being generated because of a lot of activity in the scene, that's when the arbitration schemes can lead to event collisions, it can drop packets, and sometimes it can lead to like race 22 conditions. They can get stuck. A request is never acknowledged, and hence no further requests can be made. So there are good and bad here. So the EDVS is a completely asynchronous methodology to stream out the visual events only when they happen. The downside, another thing is once we send this event stream out, what does the downstream pipeline do? There is most of the cases, the downstream pipeline is accumulating these events back into a frame, which I feel is it defeats the purpose of losing all the temporal resolution that you're getting, and you're just accumulating it back into a frame before you do any further post-processing. So that's one thing that's stuck with traditional computer vision folks is they have to see frames. They can't imagine doing any image processing without frames. So that is something that is still, I think, it's a position that's not changing. People are not ready to think beyond frames when it comes to computer vision pipelines. So what I did in my PhD is propose a hybrid vision sensor, the query-driven dynamic vision sensor. So what it does here is it takes kind of the combination of features from both the previous architectures. I do frame scanning. I go back to synchronous scanning. I scan them with clocks, row and column scanning, but I do it with a much higher frame rate or much smaller delta t. We can do it at the first prototype could do up to 400 frames per second, and now the second prototype that I'm having can go up to 1,000 frames per second. So we can scan frames much faster, but these frames only have events, right? Only the pixels that gave an event, on and off event, it's populated. And all the other pixels that do not report an event are not populated here. So here, what the autonomy now goes back to the controller. The pixels are robbed of their autonomy out. So I query the pixels if there is an event, and only then the pixel can report if it has an event. So here it's an inversion of event reporting, right? Here the pixels can report events autonomously. They can do it whenever they see a change. Here I ask them when to report an event. I query the pixels. So that's the primary reason why it's called a QDVS. So I let the periphery or the controller or the processor decide when to query the pixels. So that gives me a lot more flexibility and control in what I'm trying to capture. So, and it also keeps the pixel design much more simpler. It's almost similar to the APS pixel now, with just a bunch of additional capacitors added. Of course, there are other topologies we can talk about. So I do a capacitive averaging, a weighted average with these capacitors, and then pass it on to an amplifier that can then sense it on the column. And now we don't need a to B converter here. We're not scanning absolute intensities. We're only trying to capture changes, right? So we just need a 1-bit comparator that can do an on event detection and an off event detection. So we have two phases of comparison for on event detection and off event detection.
And the reference is global?
The VREF, yes, the VREF, you can please choose row wise. So it's a common signal.
For the whether you have an on event or an off event.
Where is the past sample stored? How is it stored in that pixel, the past sample that you're comparing to? How is it stored in the pixel? Are you going to show this pixel schematic?
Yeah, I'll zoom into this in the next.
But then go on to that.
Yeah. I'll show you some waveforms on it.
So it's on the VPH node, right?
Yeah, so the VPH node can keep changing, and the VIN node is when it's reset.
Where is the memory?
VIN.
So the CPH is then the memory. The CPH capacitance detects the change in VPH. The input to the amplifier.
I mean, it looks very similar to the Sony scheme, right? In the recent ISSC papers. They also do this frame scanning thing.
Okay.
I'm just interested in the differences because the last two Sony papers also used.
Okay.
Yeah, but this principle is actually older than that. In fact, it's even older than DVS sensors, right? We had this with Udian Malik, right? In what is it, like 20 years ago? Yeah.
Yeah, this is a DDS scheme, the double difference sampling. So we are toggling VREF up and down, and also hoping the VPH is changing. So we are looking at delta VPH and delta VREF and a combined average of that. So it's a double differencing scheme that is captured at VIN. And if that, I'll show you the equation. And if that delta VIN is larger than a threshold, it can pull the column line to directly event. Okay, so the idea here is we get certain nice advantages out of doing this QDVS way of scanning. So the latency here is a medium and a variable latency, unlike the EDVS still has a much lower latency because we can scan the events as and when they happen. Here we have to clock at a much higher frame rate. At least if you do at least 1,000 frames per second, we're talking about a millisecond latency between two events reported by the same pixel, right? So if you have the same pixel giving an event again in the next delta t, we need at least a millisecond to be able to read that out.
Pretty slow.
Yes, so now my idea is to go further. So that's the second part of my talk, is go to 10,000 frames per second, and how we can do that. So, and the bandwidth utilization is actually much lower here, because since we are scanning row and clock, we don't need to track the column address and the row address. We can generate the XYTP format, but in the downstream pipeline. So the sensor, you just toggle the clocks, you know the decoder status, you know which pixel is being selected for a query. And hence we just need to read out the 2-bit event from each pixel. So the timestamp also we can now generate externally. So the timestamp is, of course, when we can have a sequential timestamp of scanning. So when we're choosing the row and that column and reading that out, we can attach timestamp to it, right? So depending on the column clock, it scans the columns out. That can also trigger a counter on the downstream, and it can give you the timestamp of that event. So the main advantage here is that it has both low dynamic power consumption and low static power consumption. So we get the advantage in both cases here, and that is probably the biggest advantage of the QDVS. So we are not scanning, we're not consuming static power at the pixel level. We don't have comparators there. We don't have a pre-amplification stage. And we also are low on the dynamic power, because we just have a 2-bit event to report on the output bus.
How much power do you spend on the periphery to do the difference in your CDS and amplifier there in the periphery?
So the only extra power you might have to do is toggling this VRF.
No, those amplifiers there, where are those?
Oh yeah. So
the other one, the top.
This one here, yeah. So this is biased with like a 200 nanoamp current. So only the column lines consume the power, right? And that's like a static power, yes. But at the pixel level itself, so this pixel is enabled through the row select. So you don't need to have this consume current all the time. So we only let this amplifier work when the row is selected. So we need to select the row and wait a little bit for settling down, and then we read that to the sensor.
But I think your comparison of the dynamic power shouldn't depend on like how many events you have. Like if you have very few events, I would expect.
Of course, yeah. So the dynamic power, unlike the APS camera, the ADC always consumes dynamic power. So in terms of the so the QDVS compares itself in the dynamic power similar to the EDVS, because only when the events happen you consume dynamic power. Otherwise, you're not consuming any dynamic power. It's only a static power, right? So we are getting the lesser static power from the APS and the lesser dynamic power from the DVS scanning systems, both available now in the QDVS.
I don't think you should overemphasize this too much, because the power consumption is only a minor component of this whole system power.
Yeah.
Yes.
It's a minuscule fraction of the total system power of the sensor, right? It just turns out to be 1% of the system power.
Yeah, depends on the
Go
whole
ahead.
system budget there.
Yeah.
Okay. So, sorry, I think, okay. So with this, the initial prototype that we had, it was a 256 by 256 QDVS array. We could get 10% contrast sensitivity, but we consume like half a milliwatt of power for the 1.2 volt supply, and we could do up to 80 million events per second. So this was accounting for a 6.3 picojoule per pixel event, which is, I think, a really good number. So compared to other DVS cameras, the QDVS can give you almost 20x reduction in power compared to the same resolution, scale with the same resolution, and 20x increase in pixel density, because we are now looking at a simpler pixel design than the DVS cameras. So we did several things to get the power consumption down. We did complete low voltage subthreshold analog design throughout. We made sure the scan energy, even through the column lines, the column lines are clamped at a particular voltage. So we don't see any FCV squared loss on the column sensing lines. We only sense the delta peak, right? So it's almost, the scan energy is almost zero when it comes to directing the events out to the column. So we could even do supply voltage scaling down to a 1 volt in a 180 nanometer process. So I wish I could do it in a more advanced node and scale this down further. And so this is the overall.
You won't be able to. to get the low power, the more advanced node, because both transistors will be on. So they usually works at 180 nanometers because the crystals are apart.
Yeah.
Then
the
you can
decay.
go one on and one off. So
Yeah, of course, not the deep submicron nodes. Yeah.
it's all those. Yes.
Yeah, okay. Yeah, let me not overemphasize on the power, it's just the functionality is different here. You get a frame of events that can immediately lead to a lot of applications. So yeah, we do periodic scanning, we scan through the rows and columns, and the row decoder selects one row at a time, and then the columns are read out parallel. And then the pixel in the selected row can rise an event, whether it is increased or decreased over time. And on and off events are determined using this VREF voltage that goes up and down. Let me show you that. Oh, this is the pixel equation here. So the delta V in voltage is now a capacitive division, right, between the CPH and the CREF capacitors that detect the delta VPH and delta VREF. So if this weighted average delta V in turns out to be higher than an epsilon, we can call that as an on event, and if it's less than a negative, the decrease is negative and sufficiently large, we can call that as an off event.
So to do that, and you said you have 20%, the comparator must be low. What's it? Where is the comparator?
That's the column.
That's the column. So you really put one from a big, good comparator.
Yes.
Dynamic comparator with zero offset, whatever to
Yes,
zero.
exactly. Yeah, we have to do that.
I see.
Yeah, but that only consumes like a few hundred nanowatts of power because it's a voltage clamp line. Yeah.
Per column.
Yeah,
per column.
column.
Yes. Yeah.
Yeah, it's not in the pixel, so it's still a lot.
I know, so it's not n square the same, but it's still okay.
So yeah, I think I'll go. So this is the overall architecture. I'll probably skip through this a little bit fast. So we have the column detection circuit, which is we have a sensing amplifier, the column sensing amplifier, and also a clamp to keep the voltage swing controlled. We don't want really high swings here, so that we can settle down faster, and detect using a dynamic comparator to see if there's a event actually happening. So we have an on phase and an off phase. So we have a polarity variable that goes on and off, 0 and 1. And we can detect the event in each phase. And then we have a bunch of digital readout logic with standard cell gates to load the event into a latch. And then we strobe that latch to load it in the output bus. And the tri-state buffer, which drives the output bus, can now be activated by the column. When the column decoder is selected, the data is loaded on the output bus. So that's yeah. So this is a overall readout diagram. So we can reset the pixels using a global reset, and then the row clock switches to the next row. And once that row is selected, we have this on phase and an off, on event direction phase and off event direction phase. So we have two detect signals to detect the events in the corresponding phases, and then we load the event. Once the event is detected, we strobe it onto the output bus, and when the column select traverses through the columns, it can load that onto the data bus, and we can read it out. And that cycle can repeat for the next row. So this is row 1 and this is row 2. So just repeat this tiny diagram again and again. So this is some characterization results. The waterfall plot we got with the QDVS. We could control the delta VREF going up and down at different voltages, and be able to see if we can get the entire frame to switch to off event frame and a no event frame and an on event frame. And some of the sample outputs I have. So this is like a hand wave and some LED rings going around. And so the output looks similar to a QDVS output, sorry, the regular DVS camera output, but now I've been scanning frame of events out here. We could do some gaze tracking as well with, we had a prototype that we could place it and track the gaze of a person sitting in front of it.
Can I ask you a question about that?
What was the situation here? You had a dark hand on a white background or something?
Yeah, here I had a brighter background. So
Brighter
it was doing the reverse, yeah, yeah.
Okay, and for that disc, is that a black ring or something? A black ring that's moving? Is it a black ring that's moving?
No.
So white ring,
Yeah, it's a circular LED array that's moving.
LED array?
Yeah, it has many LEDs, many LEDs on a circular array.
That explains why it has that funny pattern in it?
Yeah, so this, that here you can start seeing the frame scanning limit, right? You have to scan at higher frame rates to be able to not have that.
So a ring
ADS.
of on LEDs against a dark background.
Yes.
Okay. Oh, I see, it says LED right there.
So why do you have hot pixels? I can see you have some pixels that are always on.
Yeah, so that we see it's because of the sensitivity mismatch. So
But now you have a very good comparator, not the periphery.
Yeah, but still the pixel design itself, we use MOS caps. We use MOS caps to do the double differencing, and that have limited linearity range. So that could lead to some of these.
Wait, there should be no mismatch sensitivity here, right?
Yeah, but why are some pixels stuck at on or off? I think that's supposed
Where?
some pixels are always white. Yeah, right. So
Oh, there. I see. Yes, a few. Yes, yeah. Okay.
Yeah. So the power scales now with events. So this is a nice linear curve we get when we have more events, we consume more power. So the dynamic power scales really well here, and that leads to the figure of merit that we got. And we compare that with all the other DBS cameras out there. I think the figure of merit, which is the energy efficiency metric, we got the lowest picojoule per pixel event. And I think so far we are still the lowest here.
What limits the dynamic range in this sensor?
Yes.
Quite low value?
Yes, so the dynamic range is low because we are using just a
Passive.
Yeah, passive photo direction. So we need to do an active photo direction to do that. So that is one thing that we want to fix.
But why does that passive limit your dynamic range? It's still logarithmic. It's still logarithmic over 6 decades.
Yes, but the settling time is different. So I cannot scan a dark current, a small current at 100 frames per second, right? So I didn't change my frame rate.
Or the impedance gets too high to drive the capacitor.
Yes, exactly. So the settling time I have to wait longer.
Okay.
And then yes, if I wait longer, I think the dynamic range is technically higher than what I. So some of the simple applications I built.
Just for the record.
Yeah.
I want to point out that there is a digital query-based DBS that has 24-bit dynamic range.
Okay.
Dynamic range. No,
Dynamic.
No, it's not gonna see 24 bits over.
But there's a single delta running at 200 megahertz.
But it's still
Whoa.
slow when it gets.
Single electron sensitivity. Yeah, you always discount that. You should really put it on the list.
I haven't seen any video from
it.
I'll show you the video afterwards.
Prove it with HDR video, high-speed HDR video. Don't believe it.
Yeah.
Totally. Yes, man. This is really 10 years old.
Yeah. So I did some simple applications with it. Since now we are getting frame of events, we can just do traditional computer vision stuff. So we can implement a CNN to do always on gesture recognition, right? So I just I had my own training data set compiled with just my gestures, and I could start predicting with a much smaller network here. We don't need to do any background removal or contour extraction that might be needed in an APS camera. We don't need to do any frame reconstruction or event accumulation or a spiking CNN here. We can just do a regular CNN. And with just a few parameters, like a few thousand parameters, I could get pretty nice accuracy here. But of course, it's a toy data set. I should be doing it on a much more rigorous data set. We could do motion detection. We can track the on edges and the off edges, and could almost pretty instantly direct the direction of motion, right? So we can actually direct motion even with a single frame in this case, because we know which direction the object is moving. Again, we don't need to do any event accumulation or motion vector estimation. And we could track multiple objects now just using the k-means clustering. We can track laser dots moving around pretty actively. So we can use this for traffic monitoring or surveillance applications. So again, we get the low latency here because the frame of events already given to you. We can start processing it directly. And I was excited with this, took the prototype with this exact laptop onto the I-5 highway back in San Diego, and I could track traffic moving on the highway. I was able to box them. So this is a very rudimentary clustering algorithm. I haven't done a better job at that, but it can like distinguish the different objects in the scene. Okay, so with that, I want to move to the next part of my talk. This is the last part, I think, before I talk about the next year's plan. So this is a camera architecture study that I wanted to present, and I want to hear your thoughts on that. So what is the motivation here? Is that if you want to have applications in motion detection or object tracking at extreme speeds, really high speed, fast moving objects, we want to do like throughputs of giga event per second, right? And at a higher resolution, so greater than 1 million pixels. So this is where none of the, all the vision sensors I've discussed so far, none of them can meet this criteria. So because ABS cameras cannot do more than 100 frames per second, because you're going to lose, and you're going to be a lot more power consuming. And DVS cameras again cannot scale well beyond multi-million pixels and be able to still arbitrate and asynchronously scan those events out, because the arbitration stages are logarithmic, right? So the delay propagates exponentially, and then we get events colliding, and we get lost event packets. So here, what I explored is this GALS event scanning scheme. It's a globally asynchronous, locally synchronous scanning scheme that actually combines the advantages of both the APS and DVS cameras. Just like the QDVS optimized the pixel to be a hybrid version, the GALS scheme, the GALS event scanning scheme is a hybrid scanning scheme that does partly synchronous scanning, like a frame scanning measure, and partly asynchronous handshaking, like a DVS scan. But by combining the both, we are able to push this limit to much higher resolutions and much faster readouts. So this is kind of the architecture I'm talking about, a pixel array that is locally synchronous. So we are going to organize the pixel array into multiple grid of tiles. So I'm going to partition my image sensor array like into multiple grids, made up into a grid of tiles, and each tile now will be scanned synchronously. Okay, and now within the tile we do the row column scanning, and only one event can occur from one tile at a time, right? And that will now be reported asynchronously onto the next level. And now we need to do asynchronous handshaking between the events at the grid level. So by doing this combination, we are able to show that we are able to go much higher in terms of the throughput and also scale to much higher resolutions. So I formulate the governing equations for studying this different architectures, and we did different partition sizes, like what is the ideal partition size? How many tiles we need to have to be able to meet the target that we have in mind.
So you're doing small arrays of pixels and you're doing query.
So the local synchronous, yeah, it's query based. So the local synchronous scanning is like query based, but globally, the grid level, we do asynchronous handshaking.
And why do you do that at the global level, asynchronous?
Yeah, I'll show you that. So we can do it. So if you want to do query-based synchronous scanning for million pixels, you're going to take time, right? Each row needs to be scanned for a few microseconds before we move on to the next row. And we cannot now keep doing it for millions of pixels. Okay. I want to do it at 10,000 frames per second. Yeah.
And so at that point, you're going to do asynchronous because.
Yeah. So, but again, just doing an asynchronous multi-million pixels again has a problem with arbitration scheme that can.
But it doesn't. We just built a 4 megapixel event-based camera with
Okay, what about higher? 10 megapixel, 100 megapixel? Can you go higher?
Yeah, I mean, because of the way you do the asynchronous routing.
What about the static power?
Very little, the whole thing is 1 watt.
1 watt?
Yeah.
Okay. Because the pixels are pretty large in asynchronous DVS, right? So the
No, man, you build a NOC, an asynchronous NOC, or a balanced NOC. This is really a type of project.
okay. Okay. The NOC part we can discuss later, but
Well, then, instead of doing
Yeah.
column and row arbitration, you do an H3 arbitration
okay.
of the pixel.
So what does a pixel have? Do you have comparators in the pixel? Do you
Yeah.
have
Also, we have a processor on the pixel that
Yeah,
processes events.
so that's going to take up a lot more power, right?
Not really, proportional to the events.
Okay. So there are no events, there's no power consumption at the
No,
pixel level?
no.
Okay. Let's talk
Anyway.
about it.
Go on.
Okay.
I mean, this is a general question, right? So if you have a truly event-driven sensor, an asynchronous sensor, it consumes power all the way, all the time waiting for an event to happen, right? I mean, you need to have a bias there to have enough response time when an event happens, and so that you may get several hundred nanoamps of current if you want to get microsecond time scales, right?
As I said before, power is overemphasized. Let's just.
And as you know, that power is only 10 nanowatts.
Yeah, but 10 nanowatts times millions of pixels is a large power.
Yeah, tens of million pixels a lot. Yeah.
Okay. So here for the case study here, I took a 1 megapixel, like a 1024 by 1024 array, and tried to partition it into 32 by 32 tiles, right? So each tile consists of 32 by 32 pixels, just 1000 pixels overall, and they are scanned in a query-based fashion, synchronously using a row clock and a column clock. But at the grid level, so we have a tile giving an event that is synchronously scanned, but at the grid level, we do handshaking to read them out using a row column arbiter in this case. So the question here was, what kind of throughput can we get with this, and can we scale this even further, right? So that's the setup of the study, and we did the AER representation at the top level. We just use Muller C elements. And,
So
very simple.
to understand, you scan over this grid, and each time you stop at a grid cell, you read out asynchronously?
So at the bottom level, the tiles are scanned synchronously, but so within the tile, only one pixel now is queried at a time, and it can give an event, right? So there's only one event per tile at any point of time. And those events are now at the grid level are scanned asynchronously. So asynchronously globally. So any tile can give an event at any time. So and that is scanned asynchronously. So the tiles are there's no clock matching, right? We don't need to have the tiles all running at the same clock. We can have clock skew. We can have clock drift. That is okay.
But you still need to send clocks to the tiles.
Yes, of course.
So you need different clock. Where do you fit the clock drivers in this regular array?
Yes.
So
without making holes.
No. So the clocks are still on the. Okay, I get what you're saying. On the tiles that go to the So that is okay. I've not done the hardware architecture planning here. This is just a theoretical study that we did here. Yeah.
When you scan synchronously, are you scanning per pixel or per row?
Per row.
Block, I think.
Yes, you scan one row at a time.
Yeah, so I choose one row and I scan all the columns in that row, but then there's only one column selected at one point in time. So I'm sequentially scanning the column down. Right?
Yeah, you select a row, then you sequentially scan the columns of that row.
Yes.
I see. So it's a pixel at a time.
Yeah. So technically each tile can now give a event whenever one column or clock steps to the next column. Yeah.
Why do it per pixel instead of per row? Like it's you're scanning out kind of sequentially instead of groups of 32 at a time.
Yeah, we could do that parallelly too. So I'm not. That's again an assumption that we can change. Yeah.
Yes. I'm not sure if I exactly understood, but I'm a bit confused here that like on the lower level you're doing a synchronous scanning thing,
locally synchronous, yeah.
Yeah, on the higher level, you're doing it asynchronous, but on the higher level, to me, it looks like it's kind of the same problem again. You have like, so each tile here looks like a pixel would be in a classic event.
Yes, exactly.
Right?
So it's like a hierarchical representation.
Right. So, but why wouldn't you then use the same synchronous scanning thing on the higher level? Like I don't get why the synchronous scanning is better on the lower level, but it's not better on the higher level as well.
So okay, if you want to do 10,000 frames per second, what is the biggest pixel array that you can consider? So that was a start of the study where.
Right. I like splitting it into hierarchies. I just don't understand why on one level of the hierarchy you do synchronous scanning, and then on the higher level of the hierarchy you do asynchronous scanning. Why you wouldn't on the higher level as well scan synchronously across the macro pixels, kind of like that.
To simplify the design.
Okay.
No, that's all. It's possible.
Yeah, it is possible.
It's
Yeah,
possible.
yeah. It's a good idea too. Yeah.
Okay, anyway, so then what's the result of this, or
Yeah.
what's next?
So I came up with some equations here. So we are targeting a 10,000 frames per second readout for 1 megapixel resolution camera, right? So we would need 10 GEPs, 10 giga event per second to make that possible just by doing this multiplication, right? We have a million pixels per frame, and we want to scan them at 10,000 frames per second. So we want to read out 10 giga events per second. So I'm assuming, I'm just making assumptions here, which we can change, and that will affect the equations as well. So we are looking at a frame rate of an APS camera. We're assuming the pixel is selected for just 100 nanoseconds to read out a valid voltage. So that gives you a FPS equation that is 1 over the number of rows times number of columns times the pixel scan time, right? So it's a regular frame scanning method of computing the frame rate, right? So if you want to do 10,000 frames per second, you need to spend the number of rows and columns that you need to have that can still achieve 10,000 frames per second. You can now put in this 100 nanosecond there and 10,000 frames per second here. You will see that the n row times n column cannot be more than 1,000. So your array, the pixel array that can locally scan 10,000 frames per second is limited to 32 by 32 pixel array. So that is that kind of limits the speed at which we can scan. So for a DVS camera though, I'm assuming a handshaking delay of a nanosecond, which is probably going to be large. But we can again change this to affect the equation. So I have a maximum effective frame rate defined here for a DVS camera, assuming that all the pixels rise event at the same time. What will happen? We have to read out all those events somehow, right? So the maximum equivalent frame rate we can get will depend on 1 over the number of rows times number of columns and the event scan time, right? And this could also depend on an activity factor, meaning how much activity are we seeing in the scene. That can also scale depending on the number of active pixels or the total number of pixels. So here I define the event scan time to be the arbitration time and then the handshaking and the array scan time, okay? And the arbitration time itself will be depending on the number of arbitration stages we have, and the number of arbitration stages is depending on a log of the number of rows and number of columns we have. So you plug in these for the DVS camera, and then now we have the GALS scanning camera, where the NEFR equation is different because it is now 1 over the synchronous readout time plus the asynchronous readout time. So this is the local synchronous readout time plus the global asynchronous readout time. And here we'll see that it's a combination at the tile level and the grid level. The equations look similar to the above two. Maybe this is a lot of equations, but when you look at the plot, it makes a lot more sense. So what I see here is that the APS camera, when you plug in the numbers that I showed, when you plotted the frame size or the number of pixels on the x-axis and the maximum equivalent frame rate on the y-axis, you will see that yes, if you have more pixels, you cannot get higher frame rates, right? So there's a clear in a log-log plot, we see a linear decline. So the black line, which is the APS camera design, it shows that for 1 million pixels, a megapixel camera, the frame scanning rate is around 100, which kind of maps. So if you have only one single array of 1 million pixels that are scanned synchronously, the maximum frame rate that you can achieve is around 100, right? And now I plug in the DVS equation with initially the alpha as 1, meaning all the pixels are active all the time, which gives you another the decreasing trend that we see here. And now for again a megapixel resolution, we can see that the equivalent frame rate is lower. But of course, we are not talking about a 100% activity rate. We can say like 20% active pixels in a DVS camera. That pushes this line towards the right. Okay, and then we can now start seeing that we can scan at a little higher speed than. This is a log scale plot, by the way. So we get this advantage in the DVS camera. We get lower latency of scanning out events asynchronous. But the major advantage, okay, the target we want to achieve is the red line. This is the target we want to meet, the 10 giga event per second. So at 1 megapixel resolution, we want to achieve 10,000 frames per second. This is our target. The black dot is the target that we want to achieve. We see that either a purely synchronous scanning scheme or a purely asynchronous scanning scheme is not able to get there. Okay?
So 1 million pixels at how many frames per second?
10,000 frames per second.
I see.
Of course, it's an arbitrary selection, right?
Yeah,
most problems don't need that, right? Like driving only needs 100 hertz.
Yes, but if you want to do high-speed tracking, so that's a premise, right?
Yeah, so that's a specialized thing that needs 10K frames
Yeah.
per second. Maybe you have other things that need a million frames a second, you know?
Yeah.
So you just pick some arbitrary point just for the purpose of this study.
This is for the study of high-speed tracking. So that's why I pushed the target to the right. So we can move these targets based on the assumptions that we make. But the idea here is the GALS clearly shows an advantage where we can push this envelope much more to the right. So with the GALS architecture, we are able to read out with a 32 by 32 tile size and a grid of 32 by 32 tiles, we are able to achieve much higher readout. We are able to cross this barrier and get a much higher throughput. So we proved this in simulations as well as on FPGA that we mimic the event generation. We just created all synthetic events and then we tried to scan them out as fast as possible. We saw that the GALS scheme is able to beat the other architectures.
The others are?
The fully synchronous and the fully asynchronous.
Right. Yeah, but for the fully asynchronous, you assume a specific
compressed readout.
Yeah, and also a way of scanning out, which is a column row, which is not really what the state of the art is.
Okay. Yeah, maybe I can revise on that and see how it maps out. If you look at the NOC architecture that you have. Yeah.
I think you have to compare it with like the group readout scheme from Samsung and the fancier one from Prophecy and the latest one from OmniVision where they claim like 5 gigabytes.
Yes, and then
no, they have parallel scanning schemes. So they do synchronous scanning or for the regular cameras, but they have multiple parallel readout buses. So I'm limiting myself to one readout bus, right? Of course, if you can tile more, yes, we can scale up further. But the question is for a given constrained problem, the GALS scheme seems to perform better.
The problem I could see practical thing, any image sensor company is going to hate to do this because they hate to introduce tiles to the pixel array because it inevitably introduces artifacts to the output. It introduces some blockiness to the output that's very perceivable.
This is only the way
We're never going to do it, right, in mass production because any kind of blockiness, the pixel array has to be completely.
No, in a 3D stack.
Yes, in image sensors, at least for photographic purpose, they're not going to do that.
No, I understand the photodiodes have to be like uniformly distributed.
Absolutely uniform.
Yeah, but in a 3D stack technology, we should be able to.
We have done it in 3D stack.
Yeah.
We create uniform sampling with blocky interface readout.
Okay.
I will show you video. I
So that is possible, right?
That you asked me.
So we can do it all tile-based scanning, right? That's possible in 3D stack. Yeah. Okay, and I also did like different partitions, and so I show that the same GALS architecture with a different tile partition can give you different throughput schemes, right? So the 16 by 16 file size can now get much higher than 10,000 frames per second, but lower resolution only. So you see that it's like a gain bandwidth optimization, where how much frames we can scan and at what speed what resolution can we scan this? So we took this out and put it in a Xilinx Vivado test bench for this 1 megapixel resolution, and we synthesized spatial contrast events on a diamond pattern, right? So I had 3 partitions here, and we scanned the frames at like 100 nanoseconds per column, so 10 megahertz column clock and 31 kilohertz row clock for the 32 by 32 partition. So these values are for this particular partitioning. And for the different partitioning, the row clock will change slightly. The column clock stays the same. So I'm saying I'll spend 100 nanoseconds per clock to scan any events from that column. Yeah.
Is that a table of this?
Yes, icons last year. Icons, yeah. So I implemented AER based handshaking with Muller C elements on the grid level scan. So here you can see that within the 100 nanosecond clock.
I want to look at timing diagrams.
Okay.
Okay.
I'll just show you the output then. So you can see that the different partitions show different granularity of the diamond scanning. The 64 by 64 is scanned out really fast because there are lesser events to scan. The 32 by 32 is almost scanned. We lose some events here, but the 16 by 16 partition, we are not able to scan enough events because there's just too many events being produced at the local.
So if you're gonna do that,
yeah,
why don't you do asynchronous locally and synchronous globally?
So the idea was to keep the pixels really, really simple.
Yeah, but
And that happens in
the pixel is.
No, you're putting a computer in a pixel.
Huh?
I don't want to put. I just want a pixel to be a photo detector and a buffer.
It wants to keep the pixel synchronous, to keep it as small as possible. It makes the pixel smaller, definitely.
Yeah.
I see.
Yeah, that's all. Megapixel race.
So I get good pixel density because I keep it synchronous locally. But on the
But again, your honest question comes up again. Why not?
Yeah, why not
Synchronous, why not synchronous? Yes.
Yeah.
Why do you make the second asynchronous?
Yeah, but
People know how to make very fast synchronous.
synchronous, yeah, of course, yeah.
I would even add to that by having the smaller array, you are decreasing sparsity, right? Because the 30 by 32 pixel array very likely will have an event, whereas the single pixel might not, right? So by scanning that pixel, you actually increase the probability of having an event on the in one tile, right? And then on the level above that, most of the tiles, most of the time will have an event to report.
Yeah,
I guess.
and I must say, I'm a little bit confused as well, like, if a tile is 32 by 32 pixels and an edge passes over it, what you want to do is capture those synchronous events by the edge passing, but at any one scan, you only get one event per tile.
Yes.
Right, so you have to scan the tile, if you have an edge occupying, you'll have to scan the tile 100 times if the edge occupies 100 pixels. You know, in other words, you'll have a lot of temporal aliasing within the edge because you're scanning that edge over and over again, basically, as the tile generates the events responding to the edge. So you lose all the beautiful, precise timing
Right.
that are caused by correlated events, which is what allows you to do all this tracking, is all this very tight spatial temporal correlation of the events. That's where all the power of this sensor really comes out for tracking, at least. It's by these precisely timed events that are correlated in space and time.
Okay.
And by tiling it like that, you lose that, right? I mean, you kind of lose it to the extent that you're reduced to scanning this. Maybe you're going at 10 kiloframes a second, but still, you have to scan it a lot of times if there's structure that you're trying to capture.
Yeah, see, this is the absolute maximum throughput that I'm talking about. But if you're talking about a more practical page where it's like 1,000 frames per second is enough.
Yeah, but then you still get one event per tile per frame.
So I think what Toby is suggesting, when you give evaluation metrics, you should use a set of stimuli that correspond to natural stimuli.
Natural stimuli.
Or stimuli you're gonna encounter in a set of test cases.
By the way, I don't know if you guys recall, remember when I showed you the Sony architecture like a couple of weeks ago? Probably nobody remembers it. Anyway, they adopted a synchronous readout scheme like this. But they were reluctant, they didn't agree to share any video. The only people that shared video were Omnivision.
Oh, okay.
And now, I'm told by somebody else, I'm told Omnivision shared some video from their sensor, but not the raw events, the processed output. But I'm told by somebody else that they're not convinced that the synchronous scheme actually results in good, high quality DVS output because they're limited to having one event per frame.
Right.
one event. They can't, like, in other words, if they have a high contrast edge that should produce 10 events,
Yeah.
which you normally see very often in real output,
Yeah.
you'd have to scan it 10 times, you know, in short sequence to see those 10 events.
So in that case,
In other words, you would lose the events, right?
Yeah.
You have a much bigger effective refractory period.
Right.
so in that
So-
case, wouldn't having a gas architecture help, like having some basic.
Not sure, I'm not sure
no.
how.
No, the only way you help is to really create a true event-based camera at the pixel level, which is what Quadena did
Okay.
for DARPA.
Okay.
With an H tree, where you go from an H tree at every pixel. I mean,
And then that costs the area, right?
Yeah.
well, if you're doing
Yeah.
3D, if you're doing 3D,
I see.
That's the
okay.
cost the area, right? You know,
Here it was trying to reach the pixel density of modern cameras, but. I think
To
the-
do the knob.
Yeah.
To do that knob in 3D in
Yeah.
a pixel is about 1 micron square.
Yeah.
1.5 by 1.5, what is the area? 10 by 1. 10 by 1.
Not a rectangle, but yeah.
Okay, yes.
Okay, I'll probably just wrap up my talk with a short plan for what I have for the sensors topic area next year. I'm thinking we should do an open source DDS design on the eFabless Chip Ignite program. I think all of you are probably familiar with this. We have an open source CAD tool, Skywater 130 nanometer node. We have shuttle 3 to 4 times a year. I've done one last June, so familiar with the process. We have 10 square millimeter usable area, plus there's 5 Caravelle SoC. The cost is around 10,000 for fabrication, packaging, and a dev board. So if this is something that the workshop can agrees that we can do, we can try that next year. And the options for this, we can look at a Davis pixel, we can look at an 80s pixel, we can design one of these in the open source DVS camera, and or we can have we can do the QDDS pixel with the GAL scheming, but if I think GAL is not that popular now, so so we can also do a modified DVS pixel that can do both temporal contrast and spatial contrast, hopefully in a much more compact format using switch capacitor circuits and current layers, right? So
Or other things.
so yeah, so we can have different types of DVS cameras, which we can try to design, at least a small array. Yeah. So yeah, I'll probably just skip the summary. So the idea is we can design open source DVS cameras next year around, and yeah, I'm open to suggestions. Thank you.
Yeah, and high speed.
I mean, we cannot forget because I think the chip is.
No, but if you make everything synchronous, it would greatly simplify the design, especially in the workshop, because then you could do most of the design with the synchronous tools of the readout stuff. And now, because you don't want people here doing asynchronous logic design. So it's so fragile.
I think that problem is now. They went through there. So they went through that step one, like taking the time, simulating the system, simulation.
It takes like a year to learn how to design that. Like, are you talking about that somebody here can just write barrel? You have to do it in a style, design, like CSP and all that stuff. It doesn't really work for 2D stuff, that CSP stuff, maybe for industry it does, and in a skilled hand, right? But those guys have years and years of experience.